In this video, we're going to talk about Section 7.5, Applications from Science and Statistics. Starting with work equals force times distance. So if we don't move the object, then no work is done. If the force f of x is not constant, then, so we have variable force, then the work done in moving an object from A to B becomes the integral. So work is equal to the integral from A to B of the force function with respect to x. So for example, in the yellow one here, find the work done by the force capital F of x equals cosine of pi x newtons along the axis from x equals 0 to x equals 1/2 meter. So we'll get that the work is going to be the integral from 0 to 1/2 of cosine of pi x dx. Oops, bumped the wrong button. With a u substitution, we'll get, I'm going to bring my pen back up, we'll get 1 over pi times the sine of pi x going from 0 to 1/2. So that's going to be the sine of pi over 2, which is 1, so that'll be 1 over pi, and then minus the sine of 0, which is 0, and so we'll get 1 over pi, whoops. We'll get 1 over pi, or if you put that in your calculator, that'll be about 0.318. That is going to be newtons meters, which are known as joules in the physics world. Okay, now we're going to take on a big challenge. So we're going to try to do some lifting. A leaky bucket weighs 22 newtons empty. It is lifted from the ground at a constant rate to a point 20 meters above the ground by a rope weighing 0.4 newtons per meter. The bucket starts with 70 newtons, that's about 7.1 liters of water, but it leaks at a constant rate and just finishes draining as the bucket reaches the top. Fine, so we're going to break this into pieces. First, to find the work done in just lifting the bucket alone. So that's going to be just our work is equal to force times distance. So that is going to be force times distance. So the force is that weight, which is 22 newtons, times the distance, which is 20 meters. And so that will be 440, and that's going to be in joules. So there's the first part, just the bucket alone. Now, with the water alone, so we start with 70 newtons of water, and by the time we get 20 meters up, we've got no more water left. So that means that we are losing 70 over 20 newtons per meter there. So that is going to give us a negative 7/2 for the slope. So it's going to be changing at a constant rate. So we can think of then as our as the force being variable, and it's going to be the, what do we start with, 22? No, we started with 70, and then we're going to be losing 7/2 per meter. So that's going to be our force, our variable force right there. So if we're going to then find the work done, our work is going to be that integral going from, and we can check this, I like to kind of check this by when you plug in 0, then we have not moved that, pulled that bucket at all. It's got all 70 newtons, and by the time we plug in 20, we'll have 70 minus 70, 0 newtons of water remaining. So our work is going to be the integral from 0 to 20 of that 70 minus 7/2 x dx. And if you do that, I think you get a total of 700, and that's also going to be in joules. So that's how much work we're done in just pulling up the water. Now, in a similar way, if we look at the rope, it's going to start with the full 20 meters of rope, and 20 meters times the 0.4 is going to make that have a weight of 8. And so we're going to start with that, I'll call it force, is going to start with 8 newtons of rope, and then we're going to, as we pull that up, we're going to lose then, for every foot of rope, we're going to lose another 0.4 meters, or 0.4 rather, newtons of mass, of weight, of force. So that's for every meter we pull up. So at 0, you can see when we pulled up 0 amount of the rope, 0 meters of rope, we're going to have 8 pounds of, or 8 newtons of rope dangling there. And then by the time we get up to 20, then we'll have no more rope, and so the force will be 0. So the work done is going to be that integral from 0 to 20 of the 8 minus 0.4x dx. And we can do that, and I believe that turns out to be 80 joules. So then if we add all those together, we'll get the 440 joules of work done just lifting the bucket alone, plus the 700 joules of the water, and then plus the 80 joules of the rope, which means we'll do a total of 1,220 joules in lifting that leaky bucket, rope, and water. Okay. Now we're going to talk about the work done in pumping water out of a tank. So a conical tank is filled within 2 feet of the top with olive oil weighing 57 pounds per cubic foot. So that's its density of that olive oil, 57 pounds per cubic foot. How much work does it take to pump the oil to the rim of the tank? Oh boy. So we are going to imagine we're going to take that top layer right there, and we're going to try to pump that up to the rim of the tank. So let's talk about that first, that delta volume. So the volume of that slice of olive oil is going to be a pi r squared h, because we're going to think of that as being a mini cylinder of water there. And so we need to, we need to figure out, this is going to be, we need to label this line right here. So if this tank, it looks like has a height of 10 feet, and it looks like it's got a radius of 5 feet, then that means the equation of that line that's coming up through here is going to be y equals 2x. So as we look at that little cylinder of water, that is going to be delta x for the height. The radius is going to be this right here, which is that x value. So far we've got that the delta volume is going to be pi x squared, except that that's not going to be a delta x, that's going to be a delta y. So that means that we have to get this x squared in terms of y. So if y is equal to 2x, that means that x is equal to 1/2 y. So that means that that volume is going to be pi times, that's going to be 1/2 y squared delta y, or I guess we'll call that pi over 4 y squared delta y. Now that volume, we need to know what its weight is. So this measurement is going to be in cubic feet. So we want to get its weight. So we're going to call this now a delta force, the delta force. So we're going to take that volume, that pi over 4 y squared delta y. So that's going to be some measurement in cubic feet, and we're going to multiply it by that weight density, it's called, the density, the weight density of that olive oil. So that's going to be in 57, and that pounds per cubic foot will, the cubic feet measurements will cancel, and so we're going to get this 57 pi over 4 y squared delta y is going to be our delta force. To get then our delta work, we want to take that delta force and we want to multiply it by that distance. Then we're going to have to pump that out. And so that distance, so if we think of this yellow as being the xy axis, then this distance up here is going to be the y value of that slice. And so the distance we want to pump it is going to be this height of the tank, 10, minus the y value that is the height of that slice of water. And so that's going to make our delta force be the weight, that's the force. So our delta work is going to be our delta force, which is that 57 pi over 4 y squared delta y, and then times the distance, which is going to be 10 minus y. That's going to be the work done in moving that one slice of water all the way up to the rim, and then we're going to do that repeatedly for these different slices. And so as we sum those up and let the delta y to go to 0, our work is going to become, let's see, we can pull out the 57 pi over 4. The integral, we'll come talk about the limits in a moment, is going to be y squared times 10 minus y dy. Now we are going to be taking those slices, even though we're taking it all the way up to a height of 10, these slices that we're taking here are going to only go until we're within 2 feet of the top. And so that means we're going to add those up going from 0 to 8. Hopefully that makes sense. We can do that one by hand, or you can use your calculator. I think we get on your calculator, it's going to be 30,561, and that's going to be, the units there are going to be foot-pounds. That's a work unit there. Tough question, tough problem to visualize. This is one where you really have to use your skills at describing what's happening on that differential level. And do some more of those really tough ones. So let's take a look at this idea of fluid force and fluid pressure. So dams, this is supposed to be, this yellow thing is supposed to represent a dam, and it's holding back this water like in a reservoir or something. So dams are built thicker at the bottom because the pressure increases with the depth. So as you go down, just imagine diving into a pool. If you've ever done that, as you go towards the bottom of the pool, it starts to make your ears hurt because that pressure is increasing. That fluid force, that fluid pressure is increasing as the depth increases. So I think kind of remarkably, the pressure at any point on that dam depends only on how far below the surface the point lies and not on how much water the dam is actually holding back. So if you have some reservoir that goes back into some canyon for miles and miles, the pressure and that force on the dam has to do with the depth, not the total amount of water that's backed up all over there. Kind of surprising, I think. In any liquid, the fluid pressure, that is the force per unit area, is like pounds per square inch, you might think of, or square feet or something like that, at a depth of h is given by W times h, where W is this weight density again. So it depends on the density of that liquid times the depth then, that how far below the surface are we. And that will give us then something like a pounds per square inch. So if you take your weight density, which is this pounds per cubic foot, times the depth, what you get is pounds per square foot of pressure. Okay. Now, this is kind of an amazing example. I think this is actually true. In 1919, a 90-foot high, 90-foot diameter cylindrical tank of molasses exploded in Boston. Molasses flooded the streets 30 feet deep. What a horrible way to die, to get crushed or drown in molasses. Anyway, Part A, given molasses is 100 pounds per cubic foot, that's its density, that's its weight density right there. What is the total force exerted by the molasses on the bottom of the tank? So we want to first get that pressure, think of like pounds per square foot. So we're going to take that weight density, 100 pounds, and I'm not going to write the pounds per square foot, but we're going to get that weight density is going to be that let me back that up again. So we're going to call that, what did I use for a letter there? So we're looking for, struggling with my pen. So we are looking for this right here, this fluid pressure. What's the force per unit area? And that's going to be the weight density times that depth, times that height. So our weight density was that 100, and we're going to multiply that by the depth. And since the bottom of our tank, it's 90 feet, then we are getting 9,000. That's going to be in pounds per square foot. So that's what we've called that P. That's our fluid pressure. And then so that pounds per square foot, we want to multiply by the area. So the force is going to be that pounds per square foot times our area. And since the area is a circle and it's got a diameter of 90, so a radius of 45, then that force is going to be that 9,000 pounds per square foot times pi times 45, which is the radius squared. And when you do that, I believe I have this written down there, it's going to be a lot, as in 57 million, if I can read my writing, 255,526 pounds of force. That's a lot. So the next question, part B, asks, what is the total force against the bottom foot-wide band of the tank wall? So we're going to imagine now, so this thing is going down, the bottom foot-wide, that's going to be 89 feet, and then we're going to go down one more foot to there. So we're looking at the force exerted on that band. So if we imagine a little thin band right there, so the force that's going to go against that is going to be we need first the pressure. So the pressure is going to be that weight density times the height. And so that is going to be the weight density times, and our height is going to be that, we can think of it kind of like as a y sub k, if we're going to think first in the discrete sense. So we're going to take this one little slice, which is going to be that y value of that depth going down, and then we're going to take that. So that's going to be that pressure. That much right there is our pressure. And then we're going to take that times the area of that strip. So if you slice that strip and unroll it, then you're going to see that it's really just a little rectangle, which is going to be a 2 pi r, and then times that delta height is going to be that the width of that rectangular slice there as we cut that and unroll it. So that's going to be a 2 pi, and the radius we know is that 45, and that thickness there we're going to call a delta y. So we have our weight density, which we said was 100, and times that y sub k, that's going to be our that pressure, that fluid pressure, and that's going to be times that little, so this is like our pressure and this is our delta area, and our delta area is going to be, it looks like 90 pi, and then we're going to have a little delta y is going to be our thickness. That's the part of the area measurement. So this is going to then become that 9,000 pi, and then times our y sub k delta y. And then we're going to turn this then into a integral. And so we can, I'm going to pull the 9,000 pi out. So we'll bring out that 9,000 pi. Now the integral is going to go from 89 to 90, since we want that bottom depth, so that bottom foot wide depth, and then we just have the y dy. So if you do that and punch it into your calculator with the pi and all that, you get 2,530,553 pounds of force that are being exerted on that bottom foot wide band. Okay? All right. I'm going to talk a little bit now about normal probabilities. So the probability that a clock randomly stops between 2 o'clock and 5 o'clock is, what do you think? Well, if you think about that, you might say, well, 2 to 5, that's 3 hours. 12 hours show on a clock. 3 out of 12 is going to be that probability, which is 1/4, and that's correct. So the probability is 1 in 4. But let's talk about a little bit how we might define this in a way that can help us perhaps answer some other complicated problems. So mathematically, there's an infinite number of times between 2 o'clock and 5 o'clock that the clock could have stopped, and an infinite number of times between 0 and 12, those times that show on the face of a clock. So the ratio of infinity over infinity can be tricky. A nice way to represent this is to represent the infinites is using area. So if you take an area of 1, and that's going to be the key in a probability, and spread it evenly from 0 to 12, you get this kind of thin rectangular strip that you can see in the green here. So again, you see it's a 1/12 in width, it's got 12 length, and so that makes it have an area of 1, representing all the possibilities of when the clock could have stopped. So if you look at that interval between 2 and 5, whatever that may be, then that area from 2 to 5 would be that 2 minus 5 is 3 times 1/12 is 3/12. So that area is 3/12 or 1/4, and that's a nice way of getting at the probability. So we get this idea, a probability density function, sometimes called a PDF, is a function with domain, all real numbers, and that's one of the characteristics it has to have, and another is that it has to always be greater than or equal to 0. So we can't have a probability that is negative. So the values of f of x are always going to be greater than or equal to 0. the domain is all real numbers. And the other one is when you integrate over that domain of all real numbers, that integral has to be equal to 1. So those three characteristics make a function a probability density function. So using this idea on our clock function, we could say that our f of x is given as a piecewise function is going to be 1/12 from 0 to 12 and 0 everywhere else. And so then we get a nice way of talking about the probability that a clock stops between 2 and 4 is that integral from 2 to 5 of the probability density function, and in our case 1/12, and so that's a nice way of showing that we get a 1/4. So this idea of integrating a probability density function from these boundary points, the 2 and the 5, are an idea that we're going to take into a more complicated setting. So if you're a stats person, you've heard a lot about a normal curve or a bell curve. It allows us to describe entire populations based on statistical measurements taken from a reasonably sized sample. So measurements that we need are going to be the mean, which we represent with this Greek letter mu. It's a fancy looking M, and the standard deviation sigma. That's a small case sigma. That's, I don't know how you would describe that. And our calculators will call that x bar for the mean and s for the standard deviation. Now, from Gauss, that French mathematician, we get a remarkable formula, the normal probability density function. It's also called a Gaussian curve, named after Frederick Gauss, the guy that came up with this, for a population with mean mu and standard deviation sigma. So it's given by this kind of messy looking thing, f of x equals 1 over, there's the sigma, that's our standard deviation. The square root of 2 pi comes from the area underneath that curve to make it be 1. And then we have e raised to the negative x minus mu, which is our mean, squared over 2 sigma squared. So if we have time after the AP exam, we might explore this some more. But in general, this formula works for any normal curve, and normal curves will be different depending on what their mean is and what their standard deviations are. So it's kind of interesting to note that the mean is going to be this part where we get the peak. That's where the highest probability is going to occur. These sigmas, this standard deviation, is going to be that distance that we go on either side of the mean. And that's where we get inflection points on those curves. So here's a bell curve. So the bigger or smaller the standard deviation is, it will horizontally shrink or stretch that normal curve. And the mean is going to translate where that peak occurs. But it's still that same basic bell-shaped curve. So our parent function in all of this is y equals e to the negative x squared. And the rest of that stuff is moving the peak, the mean, the highest point, the maximum value. It just moves that to where the mean is. And then depending on what the standard deviation is, it's going to either stretch or shrink where those inflection points are. And the over square root of 2 pi makes sure that the area under that curve from negative infinity to infinity is 1, so that it is truly a probability distribution function. So they make a big deal about this. And if you're in stats, you've heard this already. The 68, 95, 99.7 rule for normal distributions. So given a normal curve, whatever its mean and standard deviation are, then the idea is that 68% of the area will lie within one standard deviation of the mean. So the probability that somebody gets whatever in between one standard deviation of the mean is 68%, roughly. That's not exact, as we'll see. So, this, for example, if this was all ACT scores or something like that, then the probability that you get an ACT score within 1 standard deviation of the mean is 68%. The probability that the data lies within 2 standard deviations of the mean is 95%. So 95% of that area will lie within 2 standard deviations of the mean. And if you go out to 3 standard deviations from the mean, then the area under the curve within 3 standard deviations, or the probability that that whatever happens within 3 standard deviations, is 99.7%. So something that is outside of 3 standard deviations of the mean is really rare. Either exceptionally good or exceptionally bad, I guess. So here's some examples that we can do that we'll use for this. The first one is the telephone helpline here in red. So suppose a telephone helpline takes a mean of 2 minutes to answer calls. So on the average, they'll answer your call within 2 minutes. If the standard deviation is given by sigma equals 0.5 minutes, then 68% of the calls are going to be answered between 1 standard deviation of the mean. So that would mean between 1.5 minutes, that's 0.5 less than the mean, and 2.5 minutes, that's 1 standard deviation to the right of the mean. So 68% of the calls will be answered between 1.5 and 2.5 minutes. 99.7% of the calls will be answered within 3 standard deviations of the mean. So that would mean 3 standard deviations to the left of 2 minutes would be 0.5 minutes, and 3 standard deviations to the right of 2 minutes would be 3.5 minutes. So that's what we're looking for there, is using that 68, 95, and 99.7 rule. Okay, now we'll talk more about the calculus part of this. So the weight of spinach boxes. Suppose that frozen spinach boxes marked as 10 ounces have a mean weight of 10.3 ounces and a standard deviation of 0.2 ounces. What percent of all spinach boxes can be expected to weigh between 10 and 11 ounces? Well, first let's figure out what our probability distribution function looks like in this particular case. So we're saying that the standard deviation is going to be 0.2, so we're going to plug that in those places, and that the mean is going to be 10.3, and so that's going to go in that place. So our f of x is going to be 1 over, that's going to be 0.2 times the square root of 2 pi times e raised to the negative x minus 10.3 squared all over, and that's going to be a 2 times 0.2 squared. So you might want to enter that into your calculator as y1. You have to be a little bit careful with that, because getting parentheses where you need parentheses is going to make a difference there. So then once we have that entered into your calculator correctly as in the y1, then what we want to say, what's the probability, what percent of the spinach boxes will be between 10 and 11 ounces, we are going to integrate from 10 to 11 this f of x dx, this Gaussian curve, this normal distribution curve with our mean and standard deviation plugged in there. And if we do that right, I believe we will get 0.933, which is going to be then 93.3% of the boxes will weigh between 10 and 11 ounces. Okay? Now, the next one is kind of interesting. It's what percent of boxes weigh less than 10 ounces. So remember, the domain of a probability distribution function is from negative infinity to positive infinity. It's all real numbers. So what we really want, but we're not going to be able to do because we're using our calculator, is we want to integrate from negative infinity to 10 of this probability distribution function that we've hopefully put in as y1. So since we can't really plug in negative infinity, we're just going to take a number pretty far away from the mean. So our standard deviation is 0.2 and our mean is 10.3. So, once you get more than 5 or 6 standard deviations away, it's going to be pretty negligible. And as long as our calculator can do this without, you locking it up, if it takes too long to try to calculate this, then you might want to interrupt it and just shorten up what that lower limit is. But you just have to pick a lower limit here. I would aim for at least 5 standard deviations away from where we're trying to get to. So if you integrate, say, from 0 to 10, I believe you are going to get something like about 6.7% of the boxes will weigh less than 10 ounces. Now, the last one is kind of a philosophical question. What is the probability that a box weighs exactly 10 ounces? Well, this may be a little bothersome, but according to what we have said, this is going to be the integral from 10 to 10 of our probability distribution function, but we know that any integral from 10 to 10 is going to be 0. Kind of crazy, isn't it? All right, very good.